Alright, welcome back. We are doing Thermodynamics 1 homework number 4, problem number 2. Homework number 4 is first law analysis, energy balance type of thing on closed systems. And so number 2 is Koretsky's 2.30. So what you have is you have an insulated vessel. So insulated meaning, it's got the thing going on here. There's a membrane. Over here's water. Over here's a vacuum. Your temperature initial is equal to 400 degrees Celsius. Is that right? It is right. P1 is equal to 200 bar. This membrane ruptures. And the final pressure is 100 bar. You've got 1 kilogram of water. Anything else I'm missing? Okay. So it wants you to find out the volume of the whole vessel, and it wants you to find out the temperature of the vessel. Okay. Temperature as soon as that finishes. Okay. And so I've drawn my picture. I need to draw my boundary. Okay, my boundary is the whole thing. Okay, and that's important. Kind of the boundary seems like an arbitrary thing, a simple thing, but this is a case where drawing the boundary allows us to do our analysis correctly. And I'll get there. So we draw a picture, we draw our boundary, and then we write down our assumptions. Okay, we're going to assume there's simple things like delta KE and delta PE are 0, or approximately 0. It's adiabatic. Okay, it's a closed system. Okay, so that's one where the boundary matters. See, well, you could draw the boundary where the membrane is. Okay, and and have, we have this is one system and then this is a second system. You got mass flowing from one to the other, but that's a lot more complicated. If we just draw around the whole thing, well then, okay, it's a lot easier to do some of the math. Okay, there's definitely no shaft work. Okay, but is there boundary work? Well, it matters where our boundary is. Now, in a piston cylinder, the boundary is usually from like the bottom of the piston to the, to the bottom of the cylinder. Okay. Here, and that boundary is changing. Here, it's around the whole thing. Now, before and after the membrane ruptures, does the volume change? No. The volume stays constant. The specific volume, well, the specific volume is going to stay the same. Well, I guess the specific volume's not, because it doesn't have access to this volume. And so, you have all this volume. It doesn't change. Okay? It doesn't change what is, the volume, the boundary does not change shape, and so there isn't any work. So there's no work, no shaft work, no work as a whole. Okay, maybe like that seems like it's going to be a really boring problem. Well, it will be in the math, but conceptually it's pretty complex, because you've got to be like, okay, should there be work here? Is there expansion? Yes, there is, but not of the boundary. If my boundary was here, and my boundary was where the gas goes, then yes, there would be work. Okay. But I don't know enough to do that math. Okay. Because I don't know the final temperature, or I don't know the final volume. I also don't know how the pressure is changing with volume. There's just too many things unknown. But here, the boundary is set, so there is no boundary work. So now it's really straightforward. You know, you got your mass balance, m dot I minus m dot E equals dm dt. Again, there's nothing coming in, there's nothing coming out based on where we drew our boundary. And so this is equal to 0, okay, which means that dm is equal to 0, which means that m2 minus m1 is equal to 0, which means m1 equals m2, which I'm just going to call my mass. Okay, so that's constant. And now I have my energy balance. I'm going to write that over here. So I have the sum of m dot I, hi plus 1 half b squiggly squared I plus gzi minus, and you might be like, well, why do you write it out this way every time? Well, that way I don't make any mistakes. I also don't apply assumptions incorrectly. Okay, you know, this looks like other problems, and that's the other thing. I don't have to memorize equations. I can be like, oh, this is a first law problem. Not this is a first law problem that has a fixed boundary that is this, 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 and this. All I have to remember is that this is a first law problem, and I let the assumptions dictate what the math is going to say. Plus q dot plus w dot equals du plus ep plus ek d times b. Okay, so those go to 0 because the change in kinetic and potential energy is about 0. It's adiabatic, that goes to 0, there's no work, that goes to 0, there's nothing coming in, that goes to 0, there's nothing coming out, that goes to 0, and so I have 0 equals d capital U dt at control volume. Same kind of math here, I'm not going to go through it, but basically I'm going to have that U2 is equal to U1. Okay. So that my energy doesn't change. This is a constant energy process. Okay. So all I need to do now, okay, now that I know it's constant energy process, now this is independent if this is an ideal gas, a real gas, or steam. And you might be like, isn't steam a real gas? Yeah, but I have steam tables. What I mean by real gas is I have an equation of state. Okay. So I have to just determine that, okay, this is steam. Now, if this was an ideal gas, I'd use delta U equals CVDT, which means, well, the temperature would stay the same. Okay. Because my internal energy stays the same and it's only a function of temperature. So, it basically, my pressure went down because my volume went up. That's what happened. Okay. Okay. Now, if I was a real gas, okay, well then I'd do a departure function and all that good stuff to figure out, okay. But I'm not, I'm steam, okay. So what I do with steam is I look things up. And so I say, at T1 equals 400K and P1 equals 200 bar, okay, U1 equals something, okay. I think it's about 2600 or something, okay. The point is, at P2 is equal to 100 bar and U2 equal to 2600 or whatever, T2 is going to equal something else. So so I'm at a case where I know my pressure and I know my energy. I just need to do some interpolation to figure out, okay, what temperature is going to correspond to that energy with that pressure. Okay. And then same thing with the volume. Once I've done the interpolation for the temperature, I can do the interpolation for the volume, and then just multiply it by 1 kilogram, and I'd get my volume in that case. So pretty straightforward. The math of it, again, is straightforward, okay? What's not straightforward is the analysis, the assumptions that need to be made, and how they affect the problem, and how, because this would be a different problem if I had work in the system. If I had work in the system, I couldn't solve it, because I'd have work, which would be PDV, and then I'd have that guy. But I wouldn't know the change in temperature, and I wouldn't know the change in volume. And so I would be without enough information.